Anyway, let's get going. Thank you so much for inviting me to this, Nancy. Appreciate it. And Sunshine, thank you as well. I'm going to talk to you about some work that I did with some colleagues from LSU, Texas A&M, Georgia Tech, and my tech here and I worked on this. And what we were looking at, okay, let's make sure I do this right.
Over on the side, guys.
Side, okay.
In the middle.
Here.
This is forward, back, and
All right. Perfect. Thank you, Nancy. All right. So this, and I'll just go back. What we were looking at is the impact of the spill on the spectrum of dissolved organic carbon that we find in Barataria Bay. And I think one of the things that is interesting about this study is that it shows something about the scientific process. Sometimes you go out there to measure one thing and you actually measure something else. And that's really what this is a story of. This is an image. I'm sure that many of you have seen this image. This is an image of the slick as seen from space on May 24th. So not exactly its maximum extent, but close to it. And just to give you a sense of the scale of the system that we're looking at. Just a little bit of data on this spill in context. We had roughly 4.4 million barrels of oil that were released into the environment between the date of the spill and the date at which the well was capped. Just to put that into a little bit of perspective, that is roughly 1 cubic football field worth of oil. So roughly 100 yards by 100 yards by 100 yards. In terms of marsh impacts, we had or in terms of shoreline impacts, we had 688 kilometers of marsh oiled, 235 kilometers of beach oiled, and 16 kilometers of other shoreline type oil. And that comes from the SCAT team. I don't know if you guys have talked about SCAT. They are the Shoreline Cleanup and Assessment Team. And essentially they go out and they survey the coast on a daily or weekly basis, and they try to visually quantify the amount of oil in the marsh, high, medium, and low, or no exposure. This was interestingly probably one of the greatest sustained media coverages of any coastal geoscience issue, which I think made it an interesting, certainly an interesting time to be here in Louisiana. One of the things that we were interested in is this relationship between the spill and dissolved organic matter. And what is DOM or DOC, dissolved organic matter or dissolved organic carbon? Dissolved organic matter, it's basically organic matter that is in such small pieces that we can consider it dissolved. It is the remains of dead organisms, so phytoplankton that is broken apart and are now just teeny little bits of phytoplankton. It could be the excretions of organisms, urine or other nitrogenous waste or something like that, and building blocks that might go into organisms, amino acids, proteins, sugars and the like that may be in the environment. So it's basically everything that's out there. We often define dissolved, sort of easy to think about what dissolved is intellectually. Dissolved is stuff that's not a particle, it's stuff, you put your sugar in tea and the sugar dissolves. Operationally though, it's a hard thing to define. And what we often do is we define things that are dissolved as material that will pass through a filter of a particular size, and things that are particulate as anything that sticks on that filter. And typically you use something like 0.45 micron is a typical area where people call something dissolved or particulate. Our original goal of this project was to understand the impacts of the Deepwater Horizon spill on the composition of DOM in Barataria Bay. And we had a prediction, we had effectively a hypothesis, and we thought that the spectrum of DOM in the bay would be driven by the oil spill. We would find either signatures of oil, oil, dissolved organic matter that was related to the oil, or we thought we would find it related to decaying marshes. The oil would hit the marsh would degrade, and we'd get exudates and degrading marsh coming off that marsh, and that's what we would see. And we'd see greater, if we went to impacted and unimpacted sites, we'd see more DOM at the impacted sites than the unimpacted sites. These are where our study sites were, okay? We had effectively two transects in Barataria Bay. We had a transect that was over here on the eastern end of the bay, and this is an area where the SCAT team reported effectively no oil. They reported that this area was clean, and we pretty much agreed with that when we were out there. This was an area in Bay Jimmy that was among the heaviest hit salt marshes along the coast. These we call this transect over here we call BU, and this area over here we call BC. I think in large part, one of the things, the distribution, just as an aside, the distribution of oil was highly heterogeneous. I think what happened in large part was we had winds out of the south and southeast that blew oil in through these passes, and then it got kind of plastered along the back wall of the marshes over here. Areas that were shielded from the wind, like some areas over here, were therefore without oil, and then areas over here that were with oil. And within these areas, the front of the marsh, the southern facing end of the marsh, was more heavily exposed than the northward facing end of the marsh. So largely wind-driven transport in the bays. This is what some of our field sites looked like while we were out there, and some of us doing work. This was one of our BC sites. So we figured we wanted a strong signal. We wanted to see if we could get a strong signal at least at one of the sites. So here we have, heavily oiled marsh right in here. We've got actually booms guiding us to the marsh. So if we figured we really wanted a hot sample, this is where we get it. This is some of us, Nelson Green from Georgia Tech, grad student from Georgia Tech, Paulina Kolick, a grad student from LSU. We're out there doing some work. Effectively, we collected water samples in a variety of different manners. This is, again, some of us out in other areas in Barataria Bay, in some of the less contaminated areas. And here, we did have some friends visit us while we were en route. We looked at the spectral properties of the samples. We looked at, actually Paulina and Rob did this, but they looked at EEMs, so emission and excitation wavelengths. So basically we hit it with frequencies of light, and we get a return from the light, and from that we can tell something about the properties of the oil. And then we can plot up, we can get a fluorescence index, so we can look at the ratios of various, wavelengths of light that either are we excited with or that are returned. And from that we can try to detect or just look for oil signals. We do see some relationship between some of these fluorescence indices and salinities, maybe even a little bit of non-conservative mixing, suggesting some kind of potentially some kind of production going on. These are, again, similar plots. These are absorbance spectrum up here on the top at 254 nanometers, which other people have suggested may have some relationship to oiling. And these are our DOC concentrations in here, again, with some relationship to salinity. These are both with the BUs and the BC transects. The short story, though, here is maybe best shown visually with this graph. And this shows the concentration of DOC with respect to our position. This is where, these are our BU sites, So our uncontaminated sites and our VC sites are contaminated sites. And the short story is, we get no difference. We don't see a large signal in the spectrum of dissolved organic carbon, either in the concentrations or in the spectral properties between some of these contaminated sites and some of these uncontaminated sites. So we tried, we put up some pretty fancy techniques, and we couldn't get any strong results. And so what we thought that was more likely the case, so that sort of made us scratch our heads. And one thing that we then looked at is just simply salinity. These are salinities in Barataria Bay during July when we were out there, and then in September in another cruise. Salinities out here are quite low in July. They're almost fresh up at these marshes. These are salt marshes. They normally have salinities that are in this range, and they were much more in that range. What's driving this? What do we think is driving this relationship? It's discharge at the Davis Pond diversion. They opened up, there are a series of diversions along the coast, or really two main ones, and a few sort of smaller ones, to reintroduce fresh water. We are losing land here, and we're losing it rapidly, and largely that's because the area is not getting the fresh water and the sediments that it needs, that are necessary to build land. And so some of the strategies to restore the coast are to partially divert the flow of the Mississippi River, bring in sediments and fresh water, and reinitiate these land building processes. I'll get you in a minute. We've got a few small experimental diversions that are open, and the Davis Pond is one of them. It's capable of bringing in about 300 cubic meters per second of oil, which
Water.
is, excuse me, of water. Yes, not oil. That would be a lot of oil. It's capable of bringing in 300 cubic meters per second of fresh water, about 10,000 CFS, so about, at max, about 1% of the Mississippi River flow. What happened, we believe, is that during the whaling event, or during the summer, you can see this is in black. We've got the 2010 hydrograph, and in the dotted lines we have the average hydrograph from the previous years. They opened up the diversion massive they opened it up to full max, and that effectively changed the entire composition of Barataria Bay. We did not. We thought that what was going to happen when we were going to replace Barataria Bay water with oil and decaying marsh, and instead we replaced. What happened with Barataria Bay water was replaced with Mississippi River water, and that's
So is this a regular scheduled
no
diversion, or
okay? So the diversion itself is in place. The diversion is
independent of the spill?
Okay, so the diversion is just it's a canal that with some gates that they can open and close. So they can, the diversion, is normally open, and it's normally open at about this level, and they are gates so they can, make it run at full speed, half speed, quarter speed. And during the spill,
achieved by having it.
the goal was to push out the oil. The goal was to reduce the residence time of water in the bay and push out the oil. And while we don't know what would have happened if the diversion hadn't been open, it's a harder thing to do.
Yeah.
But we can say that there is a link between the diversion being open and the composition of DOC in the bay, and the fact that, and probably a link that we don't see any signature of oil or degrading marsh in these settings. You have a question back there?
Oh, yeah, I was wondering, Davis Pond has sediment delivery as part of its,
Not a huge amount.
but it's written into its purpose, right? Because Carnarvon has a sediment trap on it, and
I think it's the other way around. Davis Pond is largely freshwater, but even there, the diversions are so far back in the estuary or in the bay that you're not going to get any significant sediment load through them. There's at least down to these marshes. It's tens of kilometers away from the salt marshes. So you're not going to get any significant sediment delivery. Yeah.
What's the effect of the salinity though?
That's another good question. We didn't look at, so there are some interesting biological effects. The most potentially contentious one is oysters. Oysters have a narrow tolerance of salinity, and they didn't like this. And I've heard reports that much of the oyster population in Barataria Bay died as a result of this freshwater diversion. Now, what would have happened to the oysters had they gotten hit with oil? That's another story. But they have a narrow tolerance of salinity. And I think that this is interesting because a lot of the plans to restore the coast, suggest that we should divert the Mississippi River, and there is not enough data on what will happen if we do. And this is one data set on one of the largest openings and reintroductions of fresh water into the coastal basin. It's not the only one, but it's one of the. There's not enough, so this sort of fits into that puzzle. I believe so. Also we've got. Oh no, I've got 2 more slides. If I'm out of time. Okay, so just quickly though, we did look also at the, or actually Gary came also at the populations of bacteria in the bay, and we do see some partitioning of bacteria in the bay, at least along the 2 transects, but we don't necessarily think that that's related to the oiling. We think that that may just be related to the spatial gradients in the bay. And with that, I will just say, yeah, that's pretty much what I just said. And so I'll say thanks.
Rather than give a talk on specific data this morning, which we have, but we're still working it out, but it's not in a really form that I can give it to you. Plus, I have to get permission from a lot of the co-authors because we're working hard and heavy through this stuff. What I'd like to do is give you sort of a broad overview and not just the spill, but the oil industry in general, and then open it up a little bit to questions and comments, because this is a highly complex issue. There's nothing simple about this issue. So a little bit of history, and then just a few comments about some sampling designs and that sort of thing. In the late 1800s, we found it to be a really good idea to have oil, because that's when we started using cars, gasoline-driven cars, as opposed to steam, that sort of thing. If any of you have seen the movie There Will Be Blood, it's an interesting it's not really a history of the oil industry, or early oil. In a way it is, in a way it isn't. It's not the sort of movie that you will be, after you finish going out into the street and throwing rose petals. It's really it's pretty brutal. But I guess it's an example of how the oil industry has been. It has not been kind to its participants, because it's a dangerous enterprise. So we started drilling on land in the late 1800s, and then of course once oil became a very popular source of energy, we drilled more and more and more. We took more and more oil from the land, and eventually, I guess it got to the point where our reserves on land were getting low. And someone came up in the 1940s with the idea saying, well, maybe we should drill in water. The water meant the estuaries and the inshore marine areas. So that's what they began to do, and as you may know or probably know, the inner 3 miles of our coastline are state waters, 6 if you're lucky enough to live in Texas, and outside of that is our federal waters, and that's the economic exclusion zone, which goes out quite a ways. So in the early days, we were basically drilling in state waters, and we really didn't have a heck of a lot of regulations during that time, I would imagine. I have no idea what the what the issues were, what the problems were in those days. But we went on, and in the 70s along came the EPA with a lot of regulations for drilling in waters. We started moving further and further offshore and drilling in different parts of the country. By the 90s, we had drilled on the Gulf of Mexico here, the continental shelf, from around Padre Island, San Padre Island, and that area, Matagorda Island, to Mobile, because there's, as you know, there's no drilling in Florida. They don't allow drilling in their offshore waters. We had drilled between 30 and 40,000 wells on the continental shelf. That's a lot of wells. It's a lot of pinholes. As of now, there are about 3,400 to 3,600 platforms left. They're mostly being, and we're talking about the continental shelf now, okay? Being taken, most of them are being taken off the shelf. The wells, of course, are still there and have been P&A'd or plugged and abandoned, okay? They're sealed. Many of the platforms that are out there now are beginning to go idle. They call it idle iron. It's sitting out there. You'll see a platform out there, but they're not pumping oil. There's a good reason for this, and the reason is we are running out of oil on the continental shelf. It has been predicted that we will be out of oil on the continental shelf by the year 2025. So we got about 14 years to go, which brings us to offshore, deep offshore drilling, which is where our next reserves are. And this is, oh, by the way, the oil on the continental shelf, where we are now, sort of, hey, where are we going to go for oil? The problem here is that we can't, it's not that there's no oil there, there's oil there. It's just that when you sink a well, it becomes cost effective only to a certain extent to pull it out. After you've depleted the well down by about 60%, down to 40%, it's too expensive to pull the rest of the oil out. That's when they P&A it. Now with our gasoline prices up around $3.50 a gallon, I don't know, maybe they'll continue to pump. But mostly they'll cut it off when it hits about that level. That oil that is left in the continental shelf is called stranded reserves. They're there, but they're stranded. We can't really use them right away. Doesn't mean they can't go back later to get them. It just means it can't. It's not worth it to get them now. So in comes deep offshore drilling. With deep offshore drilling, because it's technologically highly complex and because it's very expensive, only the big boys can play the game. Who are the big boys? There's 6 or 7 majors: ExxonMobil, Shell, BP, and so forth. Texaco. That's where the deep sea drilling came in, and that's why and also that's where the reserves are. The next set of reserves are all Shell. Okay. So there we have a situation where we're winding down our continental shelf drilling, and we're sort of ramping up our offshore drilling. By and large, the oil companies operate in an extraordinarily safe manner. They are absolutely petrified that something will go wrong. They have safety meetings every week. I've been at some of these safety meetings, and they are intercompany. They're not Shell having theirs and Texaco having theirs or whatever. These guys all get together to compare notes to say how they can make their operation more safe for the company and for the people. Why? Is it because they're real good guys? Well, not really. It's because of liability for personnel and liability in terms of the government. The MMS oversees them, and the MMS will clunk them on the head really hard on one of their spot random checks when they come out to the platforms. If there's one nail out of place, it's kind of like the Board of Health when they come through our kitchen. I mean, they go through it like a dose of salts looking for something wrong with it. They'll write up anything. The oil companies call this ink. They don't want ink. They don't want to be written up. Some companies are very, very good about this. ExxonMobil is one. I think they've been written up 5 or 8 times in the last 5 years, which is extremely low. And other companies, who will remain nameless, are not quite as good. In fact, they have citations which are, I think it's 2 orders of magnitude higher, 2 to 3 orders of magnitude higher. I think. Okay. Blowout valves. Things happen. What's the probability of a blowout valve going? These things are made by independent companies. They are they're tested to the hilt, up and down. They cannot afford to have these things fail. What's the probability of one going? Maybe 1 in 10 to the minus 4, 1 in 10 to the minus 5. What's the probability of 2 going? Well, just like it's a probability theory. If a gentleman wears a red shirt, here comes in today, he decided this morning when he got up he was going to wear a red shirt, and a young lady wears a red blouse. Those decisions were made independently. What is the probability of 2 people coming in here? And the probability is 1 in 5, 0.2 that this gentleman is going to wear a red shirt today. And the probability is also 0.5, did I say 0.2? 0.2, that you're going to wear a red shirt because you have 4 other shirts of different colors to wear. What's the probability that the 2 of you will walk in independently wearing red shirts? It's not it's not additive. It's not 0.4. It's 0.2 times 0.2 is 0.04. So the probability of 2 blowout valves going at the same time or in sequence with the BP disaster is 1 times 10 to the minus 5 times 1 times 10 to the minus 5. That's 1 times 10 to the minus 10. That's 1 in 10,000, 20,000.
Does the probability change if they make the blowout valves in a hurry? I mean, wasn't there something about that where they didn't need all the checks or something? So
yeah, that number.
Wouldn't that change the probability of the blowout valve blowing?
Yes. So, but in any event, there are enough series of things like that that people were asking questions about. But to get to effects and concentrations of compounds, I went into the NOAA data. The NOAA data are published online regarding the concentrations of compounds of oil, concentration of oil in the water downstream. And this was around, the blowout was in April, and these were June data. It was still running. The concentrations of many compounds, they have terrific analytical labs to look at this stuff, looking at over 800 compounds that they found. And the range of numbers was pretty low. I mean, the numbers were low, but the range was within a certain amount. Then we went out and we tested out here in Terrebonne Bay with a state-of-the-art adsorbent. An adsorbent is like a piece of cotton with some special alumina on it, and that adsorbs oil. It grabs it. It's like, I call it hydrocarbon flypaper. Okay? And check the numbers there. And I checked them against NOAA's numbers. And I said, okay, but how do they look? And when I looked out, the ranges were about the same. They were about the same. This is in Terrebonne Bay, and also in upper and lower Terrebonne Bay. And I said, well, that's interesting. I guess they should be the same, except for one thing, that their numbers were taken downstream by 2 miles of where the plume was, or in the plume. And ours were 40 miles to the west, and taken 6 weeks after the well had been plugged, had been killed. So it didn't make sense. Why would the numbers be the same? And we were looking at water column numbers. And I thought about this, and I thought about this, and I thought about this, and I thought, you know, what is this? Something silly like people playing with the numbers? Highly unlikely. NOAA they just have such a good group of people doing this stuff. Those numbers have got to be highly reliable. I checked our numbers again, worked through them again and again and again and again, kept coming up with the same thing. And the only thing I could realize, that I could come to the realization of, is it was sampling design and sampling techniques. Is it that sampling techniques being used, yes, they were different, but were they appropriate? I was using a continuous flow technique, which means you sample that water for a half hour, 45 minutes. Whereas there was a different technique, standard oceanographic technique being used near the plume, where you go down below the plume and you basically capture small amounts of water and analyze it. and those numbers were very low. Well, okay, what's happening there? Another aspect to it. A couple of colleagues of mine were diving in these areas. I'm not saying I agree with it. I'm not saying it was a good idea or a bad idea or whatever. They happened to be diving in these areas. And what they had took video in the area. Now these were areas that were getting hit by corrective, where the oil was getting hit by dispersant. And the videos show that the oil being hit by the dispersant, and this is several miles downstream in the same sort of area where these samples were being taken, were coming across as basically blobs. They were being forced down below the surface of the water, but it doesn't dissolve like like sugar in your coffee. It dissolves more like egg drops in egg drop soup. There are blobs of it that are going around. When you drop something like a rosette of Niskin bottles, which are bottles that tap close and take water at a certain depth at a certain time, it's very, very easy to miss these high concentration areas of blobs because it's very patchily distributed. So my feeling is that there's probably a problem with sampling design more than anything else. So when you look at, I know this afternoon you've got some, you're going to be looking at some papers and some data and stuff like that. There's a lot of things inside that are not immediately apparent in these papers. You think about think beyond. It's like looking outside the box while you're reading these papers. Certainly with the one we'll be looking at second, we'll be doing a little bit of that. But these are what we have to do. Sometimes it takes a long time to sit down, just think about this stuff. So look at the data and think about it, and think about it, and think about it. Just like Alex did with his diversion data, to come up with an explanation. Why are these numbers off? What's driving it? What's driving it? I've gone through a couple of different areas. There's some more stuff I could talk about, but I think I'm going to just break down, take your questions. Yeah.
What else did the videos show? And are those videos available?
Yeah, you're welcome to look at them if you want. The videos, that's one major thing that came out of it. And the other thing that came out of it was how, at a time when, after the spill, when theoretically there wasn't supposed to be any more oil around, the upper layers were pretty clearly discolored, and also you can tell, when you look at, if you have, I don't want to use oil on water, but how if you have water of, there's different temperatures, and you're looking through it, and it's sort of fuzzy. Yeah, well, that's because the index of refraction is different. And one thing that was very clear out there is the index of refraction was different, not because of temperature, between the lower layers and the upper layers of the water. It's very clear in the videos, because you start going up and you're all of a sudden have things in focus. And that's a mixture, that's basically a mixture of the dispersant and the oil. Yeah.
You're talking about the large number of wells that have been drilled out there and then capped before they completed those wells. I see the commercials that the oil companies are doing now where they show how they can figure out the flow of oil, the direction it's coming, so they don't have to do as much drilling. Does that oil intersect in such a way, is the path of this oil is flowing intersected in such a way that they have the science now where they don't have to drill as many wells and they can easily pull it all up from one hole instead of having to put all of those rigs out there now? And how concerned are you about the number of rigs out there and the long-term consequences of that?
First question first. Yes, when they drill now, they basically can go down, and then they know where the reserves are from seismics and what the shape is, and they can literally drill out from one area. So they can tap into a larger reserve or even a number of reserves from their own hole. So that means less platforms if they can do that. And also in terms of where to go with them in the long term, one of the things that I found in my earlier research is that the platforms that we have, the 3,600, not all of them, but a fair number of them, say half or a third of them, have been critical in spreading the geographic spread of corals throughout the northern Gulf of Mexico because of mostly because of the flower garden banks, which are southeast of Galveston, Texas. These are new hard substratum in the Gulf of Mexico, which have not been there. We haven't had any hard substratum like this in shallow water in the Gulf of Mexico since for the last 14 to 20,000 years, since the Holocene. So over the years, in the last 40 to 60 years, they've been colonizing these platforms. In fact, it creates a sort of a problem, a conundrum for the federal government, because they have one law over here that says you have to pull these platforms out after a year after you stop producing. And then you have another law over here that says, but you can't pull any corals out because they're protected by international treaty and also by our own federal law. So this is probably going to come to some sort of head at one point or another, maybe in the near future. So leaving.
We do have the Rig to Reef program, though.
Hmm?
We have the Rigs to Reef
That's
program.
it, that's right. We have a Rigs to Reef program which addresses that subject, but that's a deep water program.
So questions for everyone at this point, although, yeah. Nicole.
Okay, I have a question.